Linear regression is designed to solve or answer certain business questions. Let's look at some common examples. For example, how can we forecast sales based on historical sales data and marketing expenditure? Think of this problem. It is a forecasting problem, and it refers to the forecasting of one variable. Which variable? The sales variable. So this becomes what we call the response variable. But what are we using to forecast this unique response variable? Possibly many variables, such as how have sales been in the past and how much are we spending on marketing. So a set of sales and marketing variables is used to model sales of the current period or maybe even of the future period. Remember, the problem is a forecasting problem. This can be framed as a regression problem. Similarly, let's suppose that our problem is to determine medical insurance premiums, and we are going to do this by framing it as understanding medical insurance premiums for customers based on attributes of the customer. For example, blood pressure, blood sugar levels, smoking habits, etc. So the business problem here is to say, given certain attributes or characteristics of customers who may become patients, can we now determine what the medical insurance premium should be? This involves finding a relationship of these attributes to insurance premiums, ideally based on past data. Again, a problem of inputs being used to model an output. From the world of finance, to determine credit card limits assigned to customers based on past spending behavior, demographic information, etc. Again, we have inputs that are customer attributes, such as past spending behavior, gender, other characteristics, etc. In this particular application, and in the medical application and such applications, we should be careful what variables we're allowed to use, but that is not an aspect of the model itself, but an aspect of are there limitations on the data. I'm just pointing that out, despite the fact that that may not be something that we will incorporate in the model itself. It's something that needs to be decided on before the modeling process begins. Another business question might be to predict power load requirements to ensure reliable grid operations and prevent outages. 2 points to note here. 1, the word predict comparable to the word forecast. The objective in these questions is not to understand sales or power load requirements, but to predict or forecast them. And in many cases, we don't really know what the input variables are. So, for example, in the last question or the last business question, we might say, what do we need to have as information from grid operations? What do we need to know about the grid? What do we need to know about, shall we say, demand conditions of the grid? What do we need to know about electrical characteristics of the grid? That's also an important part of regression analysis, thinking about what should be the input variables. Are they available to us in a business context? Do we have to spend time and money to get it? And do we need permissions, etc., for example, as we saw in the finance and medical domain? These are all important business questions that need to be resolved a little bit before we get into answering questions of how do we predict or model a response variable, our target variable, based on other variables that we from now on are going to assume are available to us and we are permitted to use them. Once we know what we are trying to predict and agreeing that what we are predicting is a number. So the question is to predict a number, a response variable, a y. For example, sales. We now need to define what we are thinking of as the problem space. In other words, the space of variables. Space is a term that people in modeling and people in mathematics like using. You can think of space as a counterpart to what we normally think of in space. When we think of space, we think of an emptiness. We think of, front and back, left and right, up and down, the space around us. So similarly, a mathematical space of variables is created where some variables can be up and down, front and back, and take various kinds of values. So what is that space of variables within which we will be able to construct a function or construct a mechanism that allows us to take variables in the space and predict a number? Let's look at some examples. For example, in retail space, when we are looking at variables that concern a retail prediction problem. So now what we need to do is understand what is the retail number that we are going after. For example, it could be sales. But sales depends on many things. And sales in turn could also influence many things. And so therefore, the precise regression problem that you're going to solve will depend on what particular number you're going to predict. If you are deciding that the problem we are looking at is sales forecasting and optimization, then I know that the variable on the response side, remember y is equal to a plus bx, on the y side is going to be, say, sales. But I might say, in order to understand sales or in order to control sales, I need to be able to look at prices as well. And prices depend on other things that may not have much to do with sales itself. For example, costs. If our prices are very low, then there may be business implications because of the relationship between cost and price. So optimizing price may require us to look at other variables in this problem space. Similarly, we want to know who to sell to, customer lifetime value prediction. Sometimes this is called CLV. And to be able to get a sense of who to sell to, and is there a way to measure that, and what does that depend on? You can see, therefore, that this idea of a problem space becomes very important within an industrial setting or a business setting because it helps us understand what are the variables we are predicting, what is the number we are looking at, and what else should we look at in order to be able to predict that number. In practice, it is almost always the case that we do not use one regression. We use many regressions within the same problem space to understand different aspects. I gave 3 examples here within the retail domain, which is to say, can we understand our customers and predict their behavior? Therefore, can we look at what we might be able to sell to them? But can we also look at what are the valid prices that are available in order to do this kind of sales optimization? Now, this particular situation is not unique to, let's say, the retail domain. We can also look at a similar situation in healthcare, where we might say there are different numbers to look at from a healthcare perspective. We can look at medical insurance prediction problem. We can look at a drug dosage optimization problem, a patient length of stay estimation problem. Are they related to each other? Yes, they are. If a medication is given sensibly, then the patient's stay can be optimal from the perspective of the hospital as well as from the patient. We know that we do not necessarily want to overstay our welcome, so to speak, in a hospital. That's neither good for the bed availability of the hospital or for our mental well-being and for the peace of mind of our families. So we know that there is a prediction problem here that is linked to other things. The insurance company may similarly care about that as well, as it may end up paying for the hospital stay. So within this domain, there are a number of variables in the problem space that the industry may be interested in being able to understand and being able to predict or forecast. Maybe other examples as well in banking space. We saw credit scoring, the need to know who is creditworthy and who is not. In a larger space, not in the retail finance context, to be able to understand investment return forecasting. In other words, how much will an investment give back? And this is an important regression example with deep consequences, because how you predict returns will determine not just the state of a specific portfolio, but the state of many portfolios relating to what happens in an economy, and has implications for what central banks, for example, do to model interest rates. And so another kind of problem space is from, shall we say, small problems within the space, like individual credit scoring, the credit scoring for you and me, to portfolios of investments, to interest rate models for economies. This is a multi-scale problem space, becomes complicated. But these are the really interesting business problems that can be solved. And the point of linear regression is that the methods to use for these problems are essentially the same. They all are, give me a set of inputs within my problem space, and I will use them to predict a number that is meaningful for my application. Perhaps one more example from the energy sector: load forecasting, carbon emission estimation, renewable energy production estimation. Again, you can see the same pattern. You can see the patterns of various interrelated variables, the idea of being able to identify a specific number, for example, carbon emission, a major problem that we are seeing at a global scale, but also at the scale of cities, or maybe even a particular street or a part of a locality. Load forecasting, which is very important for understanding the smart city structures that many parts of the world are heading towards, and as is renewable energy. Being able to understand the problem space of this particular example is a little tricky. One reason is that this particular problem space involves things that may be rather complicated to measure. They may involve aspects, for example, of the Earth itself, of taking measurements from the atmosphere. It may also involve human behavior, like in other cases. What is going to happen to load demanded over summer, for example, in warm countries, or in winter, in colder climates, where energy production is likely to spike? And so, from in some way geophysical variables that relate to wind and solar in renewable energy, to behavioral variables in load forecasting, the problem space can become interesting indeed. And the more interesting our variables are, the more likely we will get business and technology or social value from predicting the right number. This is a big picture view. We'll look at the details of specific problems as we go along, but it's useful to think now as to what might be the problem space you are interested in looking at, or the organizations that you represent. It'll give you a sense of where the techniques we're going to talk about will be the most valuable.